sometimes there are string concatenation operations. If you collect them and put them together, you get a large symbolic expression that actually represents the query. So when you substitute the actual inputs, you get the actual query. When you substitute benign inputs, you get the candidate query. If these structures match, then it's not a SQL injection attack, and if these structures match, then if it doesn't match, then it's an attack, and if it matches, then it's not an attack. So the benign candidate query is obtained by replacing the symbolic inputs with benign inputs, right? So this is how my transformation looks. So for every string in the program, I add candidate variable. So you have a string uname, that's an input, and you have a string password, that's an input. So you add a candidate string. So this is a direct source transformation. So you add the variable uname underscore c, and you add the variable password underscore c. So now I look at every operation done by the program, and I sort of shadow the operation on the candidate input. So in this case, uname, first of all, I initialize the samples. So uname is initialized to a sample. So if input 1 is John, then sample is a string of 4 A's. If input 2 is password, that is OS, then password candidate variable for the password is a string of 2 A's. Right? So now look at how I transform. So I don't transform the condition. The condition is on the real variable. So now let's look at the body of the condition. You have the query, the delete query being computed. So we already added a candidate variable query underscore c. So we just shadow the operation, except that we replace the original variables by the candidate variable. So the original query had uname, so I replace that with uname underscore c, password with password underscore c. In a similar way, I do that for the select query too. So I just shadow the whole operation, replace the original variables by candidate variables. So now when I come to execute query, I transform that statement into a statement that tries to match the query structures of query and query underscore c. If these two match, then I execute the query. If not, I just deny execution of the query. So we've seen the basic idea behind CANDID, and now I want to give a couple of examples that show that the technique is remarkably resilient in several practical situations. So let's look at input splitting function. So what it does, this application, it takes a string like Alan Turing, and it results in a query where it splits the name into first name and last name. So it results in a query where you say select star from table where first name equals Alan and last name equals Turing. Right? So now our candidate input for Alan Turing is going to be a string of maybe 11 A's, right? So the place where the space appears is index 4, right? So now the function actually takes the first 4 characters and the last 6 characters. So let's see what the candid transformation does. It starts with a candidate input of all A's, because it doesn't know the logic of the application. It just initializes the input with a string of all A's of equal length. Now the instrumented input splitting function, what it does, it gets the value of space index because we don't transform integers. So fn underscore c is input of input c from 0 to 3, which is a string of all A's, and ln underscore c, the last name candidate variable, is a string of 6 A's. Right? So corresponding to Alan and corresponding to Turing. So the query generated will be select from table where first name equals string of 4 A's and last name is. So if you compare the two query structures, they are the same. So in a typical input splitting application, the transformation works. Surprisingly simple transformation works. So let's look at another situation where the query depends on some predicted over input. So let's say the input is John, Jane, Mary, and what the application does is counts the number of words in the application and constructs a query based on the number of words in the application. So like a natural language search, for instance. So now the query is I'm only showing the where clause here, where name equals John, name equals Jane, or name equals Mary. Right? So let's look at what CANDID does. So CANDID initializes this with a string of all A's and results in a query with exactly 3 clauses, name equals something, name equals something, and name equals something. So you have the exact number of clauses matching based on the logic of the application. So if you have 2 words, John and Jane, it will still result in a query with just 2 clauses. So it's kind of neat and resilient for these situations. So if the input is just John and Jane, then you result in a query with just 2 clauses. Okay, so this is how the implementation works. There's an original program, and then we do the CANDID transformation on Java bytecodes. Bytecode transformation is particularly advantageous because you don't require access to source code of the applications, and this is all done offline. So what you have is an instrumented web application that does this CANDID transformation. Now online, when the browser makes a request to the instrumented web application, whenever the program issues a query, we refer to a SQL parse tree checker that compares the real and candidate queries. If these match, then the query is allowed to go to the database. So we evaluated CANDID over a suite of 7 applications, and 5 of these are commercial open source applications obtained from gotocode.com, and we used it against an attack suite that had 30 different attack patterns. So these attack patterns were constructed from common SQL injection patterns that were available from certain CC advisories, and these attacks were constructed by an independent research group. And the test suite also contains benign inputs that are used to test for any kind of false alarms that CANDID may generate. And this is how we did the testing. So we ran the system, the instrumented application, on a virtual machine. We ran the original application on another virtual machine, and we ran a tester application that issued these web queries simultaneously to the original application and the instrumented application, and it classified them as attack, benign, or parse errors. And these are the results from our experiments. So as you see, first of all, these applications are fairly large, over 10-15,000 lines of code. We believe the CANDID approach can scale to applications that are considerably larger in size because it's extremely simple. And we had a number of attacks for each application, in which in every case CANDID detected all the attacks. And we also had non-attack benign strings that contained SQL injection like patterns but which were actually benign, and those did not raise any false alarms. And there were a few queries that did not parse correctly and that were directly rejected by the backend MySQL parser, and we classified them separately. So this is the performance numbers. We have all the applications listed here. So the blue one represents the original application time, response time in milliseconds. So what we did was provide a query to the web application and measure the response time. And the yellow one is the transformed application with the parse tree comparison. And the green is the transformed application but without the call to the parse trees. So as you see, the transformation itself has negligible overheads, and the parse tree encounters a small amount of overhead. In most cases, it's about 20%. So we believe that CANDID can be implemented very efficiently, and if we used a more efficient hand-coded parser for SQL, we used a very generic parser generator based SQL parser, and so there was a bit of overhead there, but we believe it can be implemented very efficiently. So after the original paper describes CANDID implementation at the bytecode level, but since the transformation was extremely simple, we could we implemented CANDID both at the source and JVM levels. Each of these levels have their own advantages, and for instance what we did with the JVM was to have a candidate string for every string in the program, not just user inputs. Now the advantage of that is that you can run your web application over this instrumented VM and not do any changes to the original application. So all you do